Morning, guys. This is going to be the first of your lectures that I record from home. I already gave this lecture to section 2, so you guys can skip it unless you just, nostalgic. But this is going to be the physics and wireless lecture, and yeah, we're just going to continue JALC-ELT218 in our own weird way. If anything, the course has become more relevant in the last week now that everyone in the world is completely reliant on computer networking to work, to communicate, to stay informed. So, hope you still take the class extremely seriously. The quiz for this should already be up. Again, Section 2's already taken it. Section 1, check out this lecture and then take the quiz. All quizzes have been adjusted to 2 attempts because I am still Professor Cupcake, I believe, as I'm known. So enjoy that leniency. You still only get 1 attempt at the exams, though. And the dates that those are unlocked should be on your D2L calendar. Okay. So without further ado, this time we got to talk about physics and wireless. So, obviously Professor Hawking's having a good time flying around, but we need to get into some more advanced concepts of data transmission. We're going to talk a little bit about signaling. We're not going to get too crazy detailed about it. We will talk about bandwidth, baseband versus broadband, physical characteristics, and the benefits and limitations, why you'd use one type of cable over another. Okay, I'm going to focus on the lecture here. So everybody should know who this man is. This is Sir Isaac Newton, who supposedly was, at the time of his passing, an 84-year-old virgin, very focused on his work, and pretty much the forefather of modern physics, which he did so during social isolation to avoid the plague. So just see if you can one-up that achievement. You should also know this guy. This is, of course, Galileo, who was suspected of heresy, vehemently, they said. Anyway, this topic we're going to explore connectors, converters, couplers, and we'll talk about a few common cabling problems. We'll talk about how nodes exchange wireless signals, and we'll identify potential obstacles. You can all recognize this physicist. This is, of course, Einstein, who was an immigrant who was just visiting the United States when World War broke out, and he decided he didn't want to go home to Hitler's Germany because he is Jewish. So he stayed with us, helped us out quite a bit. Let's see. We'll also understand wireless LANs a little better, and we'll talk about the characteristics of the various iterations of Wi-Fi. Remember, it's like anything else. We invent it, we improve it, we iterate on it. So there's wireless A, B, G. We're up to AC now. There's ACX or whatever. I think I have a picture of a current model Wi-Fi router. I honestly have to just get on Amazon every time and figure out what the latest thing is because I can't quite keep up. This picture is the physicist. This is Faraday. While Einstein was thinking up relativity, he had a picture of Faraday on his wall, Michael Faraday. So, obviously, the edgelord physicist. Okay, and you guys have already done the lab where we sort of got ahead of ourselves when we configured those Wi-Fi routers that day, but I'm glad we did now because labs are pretty much impossible. So you already know how to install and configure wireless routers. Good. And you already know a little bit about wireless security because if you remember, we set a password with encryption on, and we identified clients that were already on our network and kicked one of them off, usually my phone. So we'll also identify some other common problems, usually with reception and things like that. Oh, and this is Mary Curie. She kind of discovered, unfortunately, radiation poisoning. And the paper notes she took while doing her research are still so radioactive today that you can't handle them without wearing a suit. Okay. Analog signaling, obviously, is the kind of the old way, but still usable, still used in certain situations you're going to see here. And there's going to be some quiz questions on some fairly propeller-headed topics like amplitude, things like that. And you need to understand it, that this line here, amplitude, is from the start up to the very height of the wave. That's your amplitude, okay? And let's see, a little more detail. We want to talk about also frequency, how many times this cycles over a fixed time, okay? And the wavelength, the distance between one peak and the next, and then the phase. We're not going to get too much more detailed on this. You guys just need to basically be able to differentiate between these measures of a wave, okay? Obviously, a digital wave looks a little more boring. It's just ones and zeros. Until we get to quantum computing, this is all digital. It's just ones and zeros. On or off. Yes or no. Beep or boop. So data modulation, the way we send internet to someone's house over DSL or cable is through an analog wave, through a copper wire. Like inside that wire is just psh, and not intelligible noises to any human. And then the modem at their house translates this. It demodulates or modulates, depending on which direction it's going, into this wire. And then when it talks to your Wi-Fi router, or maybe it has one built in, that's when you're going digital. It turns that wave into boop, beep, bop, ones and zeros, okay? So baseband is signals carried on one channel. Uses the entire wire. Like Ethernet's an example of a baseband transmission. Ethernet just carries whatever's on it usually. Although it can also carry power, so that definition's a little flexible. Now broadband, again, let's talk about the cable modem or the DSL modem in your house. This could be bringing in your TV, your landline if you're over 70 years old, and your internet. And the modem can tell all those connections apart and separate them, okay? Now the reason it can do this is because it can multiplex. So you take your 3 different signals, you put them on different parts of the wire, like different frequencies on the same wire, so they don't interfere with each other, they don't hear each other, they don't even know they're there. And then you move all this information over one wire together, okay? This is the reason that your cable company will never ever stop trying to sell you all their services, because physically they just have to run that one wire to your house and they can sell you all this stuff. Sorry, I have to curse less since we're recording these now. So if they're selling you internet for $30 a month, somewhere up in their organization is a marketing executive who's saying, you're selling this person $30 worth of internet. You could also be selling them $30 worth of TV and $30 worth of useless landline. So get on it. We want $90 a month out of this wire, not $30. So that's why they're always going to push it. And you should always just say, go away. The internet's all I need. Now on to performance. When you buy internet from one of these companies, you're going to buy according to the bandwidth. You're going to say, oh, I want 100 megabit down, or I want 500 down. That's the maximum possible speed you can go. Now your throughput is the speed you're actually going to get, because you're fighting with everyone else on the internet for access at any given time. So traffic's really high right now. Everybody's trapped at home. There's 300 million Americans all on Facebook and probably, Pornhub, wherever else. So the internet's pretty clogged. So your throughput is not going to be your maximum. But you can measure it with a speed test. And during normal times, when the entire country's not on lockdown, isolation, it's stuck at home, you should expect your throughput to be 80 to 90% of the bandwidth you're buying. You pay for 100 megabits and you test it and it comes out to be 85 or 90, you're good. You're getting what you pay for. If you pay for 100 and your speed test says 50, then you're getting half of what you paid for, and there's a problem. There's noise on the line. There's a squirrel chewing on it. There's too much traffic in your neighborhood. The company's kind of not delivering on their promise at that point, okay? So that's the difference between bandwidth and throughput. And we're measuring all this stuff in bits per second. This is, a bit, either a 0 or a 1 is a bit, right? A byte is 8 of those. But when we talk about data, we're going to go in bits per second. So kilobits per second, megabits per second, gigabits per second. Now, my home internet connection is 500 megabits down. That's pretty great. So that's 500,000. Right? Kilobits. Everything goes in kind of multiples like that. So your typical MiFi or Jetpack or other smaller internet connection out in the woods, like I just tried to set up like a Jetpack at my parents' house, and Verizon limited it to 600 kilobits per second. And that wasn't enough to really watch YouTube or Netflix in HD. That strangled the connection to such an extent it almost wasn't worth having these days. Because modern internet stuff, Netflix is sending out TV in HD and 4K, and YouTube is going at high resolutions. People are sort of expecting a higher grade of internet performance than we used to. So 600 kilobits would have been awesome in the 90s or in the early 2000s, and nowadays we're like, nah, man, we need 100 megabits down, or just don't bother. So your speed could look like this. This is a PlayStation Network test. 120 down, 78 up. That's fantastic for games. That's a lot of upstream. You could actually stream like to Twitch with that. Okay? So that's good. This is a network test I did for my office at SIU the other week. 200 down, 185 up. Big corporate internet connections like fiber connections tend to be more balanced. They typically have as much up as they have down, because a big place like SIU, we don't just download, we also upload, and we exchange data with other universities. We upload. Same deal at John A. You need a high-speed connection both directions. Okay, so let's talk about the cables themselves. We call it twisted pair cable because inside what looks like just one Ethernet cable is actually 8 cables. And they're organized in pairs. They're colored, orange, blue, green, red, or whatever. And one of them will be striped, one of them will be solid. So we would call the solid orange one orange, and we would call the striped orange one orange-white. That's just the terminology. Remember what we talked about earlier in the semester about jargon. You got to use the right jargon or people won't understand you, or they'll think you're a noob. So this stuff's pretty easy to install. You can actually make it yourself with relatively cheap tools. I'll have a video on that later. And it serves a number of purposes. Now, when we use shielded twisted pair, it's just like twisted pair, but it has a metal sheath around it. This reduces electromagnetic interference, okay? This is, if you're going to take 100 Ethernet cables and lay them together, you want it to be shielded. That way they don't slow each other down with electromagnetic interference, because they've got all these waves passing through them, and that noise could spread from cable to cable, and that just slows you down. So shielded twisted pair is what you use when you're running 100 cables down a hallway to a classroom. Then once you're in the classroom, you can use unshielded to go to individual computers. Okay, you don't have to spend all that money on the metal sheath, because once you're in a room, an individual cable goes to, computer 1, 2, 3, 4. They're not all laying on top of each other, so they won't interfere. The maximum throughput of these cables is the same. It's all Ethernet. The shielded cable is more expensive, of course. They all use the same connection, the old RJ45, which looks like a big fat phone jack. And the STP is more noise resistant. That's really it. Now, none of them want to carry a signal more than 100 meters, roughly 300 feet. That's just a hard rule of Ethernet. It's a limitation of the medium. You need to go farther than that with a single cable. You've got to use fiber optic. And of course, again, like everything else, we invent it, and we iterate on it, and we improve it. So we started, back in the day, we installed 10 base T Ethernet at SIU and John A, and it could do 10 megabit, and we thought that was pretty cool. Then when 100 megabit came along, that was 10 times faster. And you see, we keep just kind of upping the ante on what the cable can hold. And these days, your organization would be in good shape if you had 10 gig from building to building. You would have pretty great speed. Okay, now the cables, the wires inside the cable have to be arranged in a particular order. You have to arrange them in the same order at both ends of the cable, or it just won't work. This is how Ethernet's built. If you don't do this right, your cable won't work, and you'll have to cut off the end and redo it. I don't know anybody that uses method A, so I tend to go ahead and put a poop emoji on that. We do B. I've always done B, although probably somewhere in the world there's a shop or a place that does just A, and they're wrong, and that's fine. They can be wrong. I don't care. It's not hurting us. If you need to connect one cable to another, you can use a coupler, like this little silver guy up here. Plug in one Ethernet cable on this end. You can't see it, but on the other end, there's another connector just like this. And then media converters. Like right here, you have 1000 base T. This is like a higher grade internet cable. This is, again, sort of performing the function of a cable modem. It's exchanging from Ethernet into another type of cable, and that's called a converter. Another thing Ethernet can do that you don't often see is it can do power over Ethernet. So this is pretty cool. It's carrying the data through the Ethernet, and it's also running enough current to power a device. One of the examples we have of this at SIU is we have in McLeod Theater, we have something like 250 actuated lights to, put a spotlight on someone or light up the entire stage or dim the entire room. And they're all remote controllable, and they're all plugged in with Ethernet, and they're also powered by that Ethernet. So there's a giant switch that not only transmits the data to these devices, and our technical staff there, the theater staff is actually really sophisticated. They have Wi-Fi in there. They have tablets controlling the audio. They're really one of the more complicated areas that I have to support at SIU, and it's really cool to work with them because of that. So these 250 lights are powered over Ethernet, and the theater technical director can sit there with his iPad and bring the lights up, bring the lights down. He can program an 1.5-hour show, and as long as the actors and the music and everything else is on time, and it will be, you can essentially automate the lighting of an entire show with power over Ethernet. It's very cool. And the little devices that go with it look kind of like this. Yeah. So, when Ethernet's not enough, you need to use fiber optic. Now, this is a cable that's sort of, I don't know, the way I describe it to people, this is not exactly accurate, but it's sort of filled with mirrors. So you shine a light in it, the light bounces down the length of the cable and reaches the other end. So it carries light through it. Where's my picture of it? This is what it actually looks like if you were to rip it open. So it's much harder to actually physically install this somewhere and use it. It's not like Ethernet where you can just kind of cut it yourself with a cheap tool. But it can carry a signal really far, and it's extremely fast. Whereas electricity moves through a cable, at half or 3/4 the speed of light, depending on the cable, you're actually moving at the speed of light, which is amazingly fast. Crosses the earth in a very short period of time. This is the sort of cables we've laid at the bottom of the ocean. Okay? It's obviously much more expensive, requires special equipment and trained technicians to do it. But you're going 100 gigabits per channel. It's amazing. Unaffected by EMI completely, so you don't have to put a metal sheath around it. And you can go 40,000 meters. That's crazy. A little bit on EMI. When you have wires in a tube together, this is kind of a diagram that the book gives us about crosstalk interference. That slide probably should have been earlier. So, loss of signal as it travels away from the source. This is why you can't go beyond 100 meters. If you do, you need to amplify the signal if you have an area of high noise or interference. Or if you want to go farther, you need to just put a repeater and send the same signal on down the line a little bit farther. Here's what that kind of looks like. You've got your voltage, you've got noise, and you put an amplifier. But unfortunately, the amplifier can only amplify what it's received, so it's actually going to amplify the noise too. Whereas a repeater can kind of clean up your signal. It preserves the signal and sends it on in its original form. Okay? That's a repeater. Latency, the delay between 2 points. Remember ping. In this example, in this little diagram, you see we're pinging from left to right, from the client to the server, and it's taking 10 milliseconds to get there and 10 milliseconds to get back. That means your client ping is 20 milliseconds. That's a great ping to play a video game on. 120 ping is where you start to feel lag and feel like you're not moving and your character's not doing what you're telling it to in a video game. 150, 200 ping and the lag is so pronounced you almost can't play. And again, this is measured in round trip time. So fiber cable problems, fiber type mismatch. this has been the theme as we build the internet out across the entire planet, is different companies, different countries, different rules, different laws. It's tough to get everybody to use the same equipment, and they have to some extent, for it all to link up together. Yeah. I don't know why this slide's in there. This probably should have been in the cable management area, but it's funny, so we'll keep it. But if you were going to troubleshoot a room like this, if you get sent into a room that looks this terrible and nothing's labeled and everything's kind of mismatched and you see cables running from one side to the other, it looks like someone's solved 100 problems in here with workarounds and documented none of it. So how are you going to figure out what is what? Well, you're going to use some troubleshooting tools, such as a tone generator or a tone locator. And the way these work is sort of trial and error. You hook up the tone generator to one end of a cable, and then you go to the other end where you have 100 cable ends, and you have to figure out which one is connected to your tone generator. Well, you use a little listening device, and you go to the other end and try every cable until you hear that tone. It just makes a boop or whatever noise on the cable, and you listen for it. Okay? For electrical stuff, you use a multimeter to make sure that you've got the right amount of current in a line. Verify that the cable actually conducts electricity. If it doesn't, then it may be damaged or just not sufficient or too long for what you're trying to do. You can tell the presence of noise with one of these. Pretty handy. When you're making Ethernet cable, unless you're a super duper pro at it, you're going to want to test every single cable. And the way this works is you build a cable, you plug one end into the little guy here, the other end into the main unit, and you turn it on, and it'll light up 1 through 8 if your cable is good. A cable will still technically work if it goes 1 through 6, but you should try to make sure they all connect properly in case you ever use it for power over Ethernet. So these are cheap. These are $10 on Amazon nowadays. Okay, moving on to wireless. So wireless is a cool thing we invented a while ago. It's generally not as fast as wired, but you don't have to really build anything. You set up a transmitter, and then your devices have wireless adapters in them, and they can talk to the transmitter. That's it. And they transmit with radio frequency waves. So a couple different bands that can interfere with other devices. More on that in a second. But they basically function just like imaginary cable. Okay? So they live on the light spectrum. Here is an unnecessarily complete example of all light spectrums. Really all we're concerned about here is this area, radio. Okay? So you can see that AM radio's a chunk down here, TV gets this area, FM gets this chunk. Then we were like, oh, TV's super important. We need to give it more space. We kind of had the same phenomenon with wireless. We gave them a tiny little piece, and it wasn't enough. And it interfered with microwaves and cordless phones, so we had to give them another piece. Okay, so how does wireless work? Well, it works great line of sight. If you're in the same room as the router with your phone or your tablet or your computer, you probably have 5 bars and the maximum speed that your internet connection can offer. If you are not in a direct line of sight from your Wi-Fi router, your signal's got to bounce off of walls and other devices. It's going to get kind of reflected and messed with. And reflection can be dealt with. You can still receive a signal that's reflected. You can kind of receive one that's been diffracted, and once it's gotten so messed up that it's not useful anymore, we say it's scattered. This will result in data errors. You just want to have a connection. You'll have 1 or 2 bars on your Wi-Fi device, and your customer will be mad and say they keep getting knocked off the internet. This is what it looks like in a room. This is kind of a helpful drawing someone did. So objects in the way, depending on what they're made of, the signal could just pass right through them. No big deal, right? Could be absorbed into them. That's bad. That means it's not going to get to the target area. Could be reflected off the ceiling here. We have some nice reflection off the ceiling. The computer's probably actually getting that signal. It's getting a little bit of this diffracted signal. And then this one over here that's getting diffracted off of this amazing potted plant, that's not helping anybody. That's just sort of wasted signal. In most cases, if this customer says my signal to the Wi-Fi router is bad, you're going to want to hang it up higher on the wall to get past this TV, because this TV I think that's a TV. It might be a mirror, but let's say it's a TV. It's got a metal plate in the back of it to shield it from interference. And that metal plate stops your Wi-Fi signal cold. So you get the Wi-Fi router higher up, then it passes straight through this, probably plaster or drywall, and then the computer's fine. Gets better reception. So placement of Wi-Fi routers is very important, and placement of the client matters too. So attenuation, this is where the signal weakens over time. Even in line of sight, eventually Wi-Fi wears out because the atmosphere slows it down. It bounces off, air particles, etc. And then noise. Signal to noise ratio is what you're concerned with. Signal is good, noise is bad. So a high signal to noise ratio means a probably usable signal. Okay? The two bands, remember I said Wi-Fi started out on 2.4, but guess what? Cordless phones were also on that band, and some microwaves would sort of spill over noise into that area. I have seen situations where people would be on their Wi-Fi and they'd receive a call on the cordless phone and it would knock everybody off the internet for an instant. Very, very obnoxious. So then we got 5 gigahertz band, and we're like, okay, this is just Wi-Fi stuff on 5 gig. So 5G, you're usually going to find, you get knocked offline less. It's got more bands devoted to just Wi-Fi stuff. This is kind of what that looks like. These are the channels that we have available to us to use 2.4 Wi-Fi. And we have many more channels on 5G. This is why if your router can do both, you're better off being on 5G. So a wireless PAN, yeah, this is just sort of a term we're not going to concern ourselves too much with. But you do use this for Bluetooth. You use near-field communications when you tap your phone on things to buy stuff, if you've started using that technology. And infrared remotes are technically little wireless PAN devices. Bluetooth everybody uses at this point, usually for headsets or car adapters or speakers, stuff like that. Bluetooth, again, lives in that 2.4 range, so it's very susceptible to getting knocked around by other devices, but it's only intended to be short range. Most Bluetooth advises you to stay within 10 to 30 feet. You get beyond that, it starts acting really weird, and devices have to be paired. And, of course, if you've ever used Bluetooth devices, they usually have to be repaired over and over again. It's really cool. Near field is the thing we use to let phones buy stuff by smacking them on things. It's always a good idea to take your $600 phone and smack things with it. But hey, it's technically a almost touchless purchase, so in these days of germophobia and isolation, it's maybe a good way to pay for things. Because your credit card could have germs on it, and if you hand it to the cashier, etc., you guys are essentially swapping germs. But if you use your phone to buy things with Apple Pay or whatever, then you're going to exchange less biological matter. Gross and cool. NFC tags, nobody uses those anymore. Okay. An ad hoc wireless LAN is when you just connect two devices together, and anything can do this. Your phone can do this. It can function as a hotspot. Your two computers can do this, functions as hotspot. One of them is like, I'm the router and you're the device, and they can just sort of trade. Basically, any wireless NIC can do this. Any device that has wireless capability nowadays usually has this functionality built in somewhere. More conventional way to do it is to have a devoted router. This is what you got in your house, right? If we look at this, is probably what your house looks like. Remember when we drew our home network maps? I said, show me your router, show me all the devices you have connected to it. You've got your Xbox, your smart TV, your laptop, your Alexa units are all connected. Alexa, cancel. Don't do that. No, stop. Yeah, careful. And this is how you're going to lay it out in your house. You pretty much want the wireless signal to be in every room. That's why nowadays Google sells this Wi-Fi router rig that's actually 3 pieces that you spread all over your house like this to bathe every room in delicious Wi-Fi radiation. I'm sure there's no negative consequence to that. One of my guys had to do this for the pig farm, I think. He's the technician for agriculture, the College of Ag, and they needed some kind, for whatever reason, they needed Wi-Fi connectivity out at the pig farm and the cow pens and whatever. So he sets up the building that has internet. He puts a transmission antenna on it, and he aims it out at the pasture where they need the Wi-Fi, and then there's a receiver antenna. And these things do just a real focused, you got to aim them at each other pretty accurately. And up to 300 feet, they sort of form a bridge between these two areas and provide Wi-Fi. Pretty cool. The standards of Wi-Fi started in '99. We had 802.11. A was sort of an experimental thing that never made it out of the lab. B is the first one that made it into public use widely. And then we moved on up the line. We kept improving the speed, the bandwidth, the actual reception and stability of it got better and better. And nowadays we're on to AC. Here's a chart of the progression of speeds. You can see we started out at 11 megabits, so very similar to 10 base T internet, Ethernet. And then we quickly jumped up to 54. Nowadays, your router can actually form multiple connections to the same device. So if your phone or your computer's Wi-Fi adapter can do multiband, they'll just go ahead and make multiple connections to each other on different frequencies to further increase their internet speed. I pulled this off Amazon. This is a pretty current router. We're up to Wi-Fi 6, AX6000. Runs 8 streams, etc. You can see all the features there. This thing is like a little computer unto itself. It has a quad-core processor, probably a pretty good amount of memory. Has USB ports. You can connect hard drives or printers to it and share them. Pretty cool. This is your kind of run-of-the-mill router these days. Very sophisticated device. We're not going to go too into detail on carrier signal stuff. Just remember the basic principle that real throughput is less than theoretical, okay? These protocols do their best to make sure your packets get there, and it's sort of like TCP/IP connectivity stuff. But you just need to remember that the maximum is not what you're ever going to get. Packets are like Frogger. They've got to run kind of a gauntlet of possible interferences and blocks. But they do still have an association. They do still have a, I'm from here, I'm going to here. They have their own information. And Wi-Fi routers have a way of scanning the area. You guys all know this inherently. You take out your phone and you hit Wi-Fi and you see every Wi-Fi router in the area. Well, that's because they're sending out beacon frames. And you are sending out essentially a probe frame saying, I'm a client looking for a Wi-Fi server or Wi-Fi router to connect to. That's how this works. The router constantly sends out a ping saying, I'm here, and your phone or your laptop or whatever sends out a ping saying, is anybody a router that I can connect to? And it puts them in a list for you, lets you connect to whichever one you want. Then you associate with it. Oh, here's just a beautiful frame. Just bonus material for you. This has really very little to do with anything. But this is what a Wi-Fi list looks like. It shows you the name of the Wi-Fi router. That name we refer to as the SSID. Network nerds will call it an SSID. Regular people will just say, oh, what's the name of your Wi-Fi? Here in this example, it's probably an apartment building or maybe a set of duplexes or something where there's a lot of, passive aggression going on in the Wi-Fi names. You give humans any kind of creative leeway at all, they will express themselves. So it's kind of beautiful. Let's see. We're not going to worry about extended service set. And when several access points are detected, and again, you guys, this is sort of inherent to you. You've grown up with Wi-Fi, many of you. And so you know that the one with 5 bars is better than the one with 2 bars. And you're going to connect to the one which gives you the most speed. Okay? So mapping a Wi-Fi network can actually be more complex than wired because anything can be connected to anything that's in range and they can see each other. It's almost better to get on the router and say, show me the devices that are attached, and then you'll be able to draw a network map because you know what is talking to what. But it's very hard to visualize initially. You walk into a room, you have no idea what's connected to what. Here's an 802.11 frame. You can see that it's still got a collection of addresses, destination, and source. And then it's got the data, just like any other kind of packet encapsulation method, okay? So when you design a wireless LAN, there's some things you need to think about. Placement, as we discussed, is important. Are you going to do one access point or multiple and kind of merge them together into one thing? You're going to name them all the same thing so that devices don't really know or care which one they're connected to? But basically you want every part of the workspace or home or whatever you're trying to provide internet to to have some level of usable signal, and placement matters a lot for that. Now, larger wireless LANs, if you're going to say build wireless into John A. Logan, you're going to need hundreds of routers. You're going to need to space them out intelligently. You can't just kind of put one every 100 feet and hope that works. You have to actually walk around and look at the lay of the land, and your network architects, when they put in your Wi-Fi, they will have done that. They'll say, oh, we're going to need one just for this area because these walls are thicker and they have interference. We can do one in this hallway. You have to space it out intelligently. You have to kind of do a site survey and figure out where you're going to build this stuff. Okay? And some of these are just going to be bridges from one place to another. Not at John A, of course, they will have run cable to every single one of them. But you, in weird situations like this, one of the weirdest Wi-Fi jobs I've ever had to do was to provide Wi-Fi cameras to my stepmom so that she could watch her miniature horse paddock from up the side of a volcano where she and my father live in Hawaii, from their house, because she had knee surgery, so going up and down the hill was not good for a while. She was specifically told not to do that, and she needed to monitor the horses because one of them was preggo. So I had to add a Wi-Fi router that was a bridge to their original router that could reach the horse paddock, and then set up the Wi-Fi camera, and now she can pull up her phone and check on the horses at any time. Although, because it's Hawaii, these giant terrifying spiders tend to build webs over the camera every day or two, and she sends my father down there to clean those off, and he's good for that. He's handy. So the next thing you need to consider, of course, is security. Even there in the remote jungle of the big island in Hawaii, we got a password on our Wi-Fi, just so nobody's on it that you don't expect to be on it. And so all of the bandwidth is devoted to what you want to devote it to. And then if you're in a workplace, like you're setting up Wi-Fi for a law clinic, there's actual legal implications. If you're setting up Wi-Fi for a doctor's office, there's HIPAA regulations. You cannot have an unsecured network where any old person can log on and look at people's files. So you have to provide quality security. And every Wi-Fi router has the ability to have a password on it. These days, they all have encryption built in, so there's really no excuse to not do it. And nowadays, they're all going to use WPA2 probably, and this is a type of encryption. So security threats to Wi-Fi, if you didn't have it locked down, people used to, in the early days of Wi-Fi, people used to drive around and scan for unlocked, fully accessible Wi-Fi networks and actually just write on the side of your building a mark in chalk. A backward C and a forward C like you see here means open node, log in, do whatever you want. We don't see that as much anymore because everyone has a password or they have guest limitations on it, like if you're at Panera's Wi-Fi or whatever. There's some other things you can do, though. You could take your evil Wi-Fi router to a place and name it John A. Logan Wi-Fi, or name it exactly after our Wi-Fi, and set it up. And people in the building might accidentally connect to it, not realizing that they're connected to you and not the real John A. Logan internet. And then you can spy on them or try to access their computers, etc. That's called an evil twin attack. You don't see that too often. The network team, again, puts in safeguards for that so they can detect whenever someone sets up a rogue AP. Like when we set up our rogue APs in the classroom that time, they knew about it. That's why I told you guys, don't put anything super offensive as the name of your Wi-Fi router, because it's going in a log somewhere that the network engineers can see. So, troubleshooting, yeah, your cable testers won't help you. You need tools that can help you monitor Wi-Fi networks. That's going to sometimes be an app on your phone. It's kind of the cheapest, easiest way to go. There are more expensive tools. If we'd been able to have our guest visitor later in the semester, I would have had our buddy Jimmy Brown bring in really fancy, expensive network testers to tell you, oh, this room has this reception, there's this interference in here, there's this frequency going on in here. They give you a full detailed analysis. But otherwise, at the very least, you should walk around with your phone and go, okay, this room I'm not getting a good signal, this room I am, maybe the router needs to be moved. So you can kind of test it and evaluate it yourself. Okay. That's enough info for this segment. You should be able to go and take the quiz, which is on D2L and available to you. Again, Section 2's already done it. Section 1, you need to take this one. And then you can move on to the next lesson after that. Now, the lab we would have done, if we could do labs, which we can't now, is to make Ethernet cable ourselves in class using the type B arrangement. Orange, white, orange, green, white, blue, blue, white, green, brown, white, brown. Which I've memorized because I've made too many Ethernet cables in my day. So, since we can't do that, you got a couple of options. I found a really good video on YouTube, and I'm going to put the link to this in the info below this video, so you can click it there. I'll also post it on D2L, and you can watch this video. It's 2.5 minutes long. It's a really good explanation of how you make an Ethernet cable. You can kind of see what's what. If you're determined to have done it yourself, this video and about $50 spent on Amazon.com will get you the tools to make Ethernet cable. You could even buy a little short spool of it and make some yourself. And a cable tester is $10. Crimpers are $20 or $30 these days. The connectors are like $10, $20, and then you just need some raw cable. So that's the way to do it. Thank you for coming to my TED Talk, and we'll see you guys in the next video.